The new pictures from the James Webb Space Telescope have stunned specialists, revealing a frightening reality about the universe. Rather than merely broadening our perspective, these photos have uncovered a disturbing truth. Our current understanding is insufficient to grasp the possibilities of the universe in its earliest stages. The prevailing theories regarding the universe's beginnings appear to be reaching their limits, prompting us to reconsider new theories about its origins. This raises a fundamental question: how was the universe shaped, and why? These discoveries challenge even the most experienced astronomers. As a result, there is a need to explore the true nature of the Big Bang and its ever-evolving complexities. It might be time to reconsider the Big Bang theory itself, as common interpretations have often misrepresented it. The Big Bang wasn't just an explosion within pre-existing space, it was the actual beginning of space itself, unfolding approximately 13.8 billion years ago, alongside matter and time. One of the key concepts in science and cosmology is the idea of a singularity, a point where gravity becomes so intense that the curvature of spacetime becomes infinite. Billions of years after the universe's creation, we now understand that our cosmic home exists as part of a vast interplay. For scientists, this highlights a crucial aspect of the universe's existence: its ongoing expansion. The universe doesn't simply drift into pre-existing space. Rather, space itself continues to expand, as supported by standard theories. The first stars are believed to have started shining approximately 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age of the universe. This was the period when the first luminous celestial objects coalesced to form mature galaxies. However, the speed at which these galaxies developed remains a mystery. A significant milestone came in July 2022, with the James Webb Space Telescope's first images revealing various galaxies, some of which existed around 300 million years after the universe's birth. Despite being much younger than the galaxies we observe today, these early systems were significantly smaller and less massive, aligning with the scientific model of the time. In the early universe, the density of matter was insufficient to create galaxies as large as those we see today. The discovery began with 6 remarkable, red-shifted, bright spots identified by the James Webb Telescope, sparking one of the most significant cosmic mysteries in recent years. These newly discovered galaxies, although similar in age to previously recorded ones, appeared almost as large as our Milky Way. This finding has ignited intense interest in Big Bang cosmology. After analyzing a series of images taken with the telescope's near-infrared camera, scientists confirmed the presence of these distant objects. Using redshift data, they determined that the light from these galaxies had traveled for more than 1 billion years before reaching Earth. Consequently, these galaxies existed between 570 and 700 million years after the confirmed Big Bang event. This astonishing discovery challenges conventional cosmological assumptions, which predicted the formation of much smaller, less developed galaxies at this stage of the universe's history. Instead, the James Webb Telescope revealed galaxies nearly as large as the Milky Way, defying expectations. The gravitationally bound stars in these galaxies had already amassed more than 10 billion times the mass of the Sun. One of these galaxies even showed signs of a mass exceeding 10 billion solar masses. However, the accuracy of this theory remains uncertain. Even if true, the mass present in the early universe would be far greater than previously predicted, deepening the mystery. The discovered galaxies challenge almost all traditional cosmological theories. If even one of these galaxies is confirmed, it would force us to rethink our assumptions about the formation of early cosmic structures. The density of matter in the early universe would need to be much higher than previously thought. Another possible explanation is that these galaxies formed in an entirely unknown way. These discoveries demand a re-evaluation of the Big Bang theory. Many astronomers are baffled by these findings, often voicing their concerns in scientific publications. Those who question current theories are frequently labeled as radical or extreme. Yet, even proponents of the Big Bang theory are grappling with unresolved questions. These include fundamental concerns. How could something arise from nothing 13.8 billion years ago? Was there a trigger for this event, or was it purely random? Stephen Hawking famously argued that the concept of time, as we currently understand it, began with the Big Bang. Therefore, this process could not have been initiated by something external or caused by an external trigger. Similar questions arise about the uniform distribution of radiation and matter across the universe. No matter where we look, we observe a similar arrangement of galaxies, nebulae, and radiation. Modern scientists explain this phenomenon through the theory of cosmic inflation. However, others have expanded this idea, suggesting that the universe has expanded in a turbulent manner. According to this theory, expansion occurred only in isolated regions, like bubbles, while other areas continue to expand indefinitely. This model raises the intriguing possibility that multiple universes could exist within these expanding bubbles, each governed by its own set of physical laws. This perspective suggests that our universe might not represent the entirety of existence, but could instead be just one part of a much larger and more complex structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe has been proposed. However, this view is far from the dominant perspective in cosmology. For example, in 1955, an article published in NASA's Star magazine suggested that the universe may never have experienced a Big Bang and that it has always existed, possibly for an infinite period. In this interpretation, the expansion of the universe would simply represent a phase in its infinite history rather than a specific event. This steady-state model, though largely abandoned by mainstream cosmology, highlights the enduring mysteries surrounding the universe's origins and evolution. Even today, cosmologists debate whether the universe has a definitive beginning or represents an eternal cycle of expansion and contraction. The idea of a multiverse, where countless universes exist alongside our own, further complicates these discussions. If true, it would imply that the Big Bang was just one of many such events, each giving birth to its own universe governed by unique physical laws. The discoveries made by the James Webb Space Telescope have reignited these debates, challenging previously held beliefs and forcing scientists to confront new data that does not align with established models. Whether these anomalies signal the need for entirely new theories or are simply deviations that will eventually fit into the broader cosmological framework remains to be seen. In the meantime, these findings underscore the importance of continued exploration and openness to alternative ideas. The universe is far more complex than we ever imagined, and each new discovery brings us closer to understanding the intricate tapestry of its history and structure. While definitive answers may still elude us, the pursuit of knowledge deepens the mystery. Some intriguing hypotheses rooted in quantum physics and string theory suggest that the universe, and everything within it, could be a holographic projection from a higher dimensional reality. While this might sound like science fiction, it is a serious consideration in theoretical physics. One connection to this idea lies in the Kardashev scale, which measures a civilization's advancement based on its energy utilization. A Type 3 civilization, capable of harnessing the energy of an entire galaxy, might possess the ability to simulate a universe with precision. This raises the provocative question: could our universe itself be a carefully constructed simulation? Proving or disproving such a scenario presents monumental challenges. Exploring the depths of cosmology and the origins of the universe takes us into realms of profound mystery and relentless scientific inquiry. The images captured by the James Webb Space Telescope have reignited debates about the very fabric of existence, challenging established theories and empowering scientists to rethink fundamental aspects of how we interpret the universe. Central to this discussion is the Big Bang theory, which remains the cornerstone of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, rapidly expanding and giving rise to spacetime and matter as we observe today. This monumental event was not merely an explosion within pre-existing space but the beginning of space itself. The notion of a singularity, where gravitational forces become so intense that spacetime curvature becomes infinite, guides how we interpret this early phase of the universe. However, the discovery of mature, massive galaxies a mere few hundred million years after the Big Bang challenges traditional notions about the speed at which cosmic structures formed. These findings suggest that the early universe possessed a much higher density of matter than previously estimated, raising questions about how such massive structures could have developed so rapidly. This compels cosmologists to re-examine the processes through which galaxies, like those observed by the James Webb Telescope, emerged so early in the universe's history. Another pivotal question arising from these discoveries is the role of cosmic inflation. This theory posits that the universe underwent a brief but exponential expansion immediately after the Big Bang, smoothing out irregularities and explaining the uniform distribution of matter and radiation across the cosmos. Yet, some physicists have proposed alternative models, such as chaotic inflation, suggesting that inflation might have occurred only in isolated regions, potentially leading to the existence of multiple bubble universes within a grander multiverse. If true, our universe would not be the entirety of existence but one small bubble within a much larger, more complex structure. This concept ties into speculative ideas about an eternal cycle of cosmic birth, growth, collapse, and rebirth. It also opens the door to the possibility that other universes might operate under entirely different physical laws, adding layers of complexity to our understanding of existence. As the James Webb Space Telescope continues to provide unprecedented glimpses into the cosmos, it forces us to confront fundamental questions. Is our understanding of the universe's origins accurate? Could the Big Bang Theory itself require significant revisions? What role do unknown or unforeseen processes play in shaping the universe? Each discovery pushes the boundaries of human knowledge, emphasizing the importance of keeping an open mind in the face of new evidence. The universe, in its vastness and intricacy, continually surprises us, revealing that much remains to be understood. The journey to uncover these cosmic truths is ongoing, fueled by the relentless curiosity and ingenuity of humanity. The discoveries made possible by the James Webb Space Telescope are not just reshaping our understanding of the early universe, they are also redefining the very goals of modern cosmology. If the early universe was more dynamic and complex than previously thought, this raises questions about the mechanisms driving galaxy formation and evolution. What factors enabled such massive structures to emerge so quickly? Are there unknown forces or processes at work that we have yet to discover? Challenges to established models. One of the most profound challenges lies in reconciling these observations with the lambda-CDM model, the prevailing framework for understanding the universe. This model, which incorporates dark energy and cold dark matter, has been remarkably successful in explaining a wide range of phenomena, from the cosmic microwave background to large-scale structure formation. Yet, the newly observed galaxies seem to contradict some of its key predictions. For example, 1. Massive early galaxies. Observations suggest these galaxies had already accumulated significant mass within just a few 100 million years after the Big Bang. The timeline for such growth under the lambda-CDM model seems implausible. 2. Star formation rates. The intense brightness of these galaxies implies extremely high rates of star formation, potentially exceeding the theoretical limits imposed by available gas and cooling timescales. 3. Dark matter's role. If dark matter played a central role in early structure formation, its distribution and interaction with normal matter might need re-examination to explain these anomalies. These inconsistencies suggest that either the physics governing the early universe is not fully understood, or the assumptions underlying our cosmological models need to be rethought. The role of technology. Advancements in observational technology, like the James Webb Telescope, are revolutionizing our ability to study the cosmos. With its ability to detect faint infrared signals from distant galaxies, the telescope is providing data that was previously inaccessible. Future missions, such as the Nancy Grace Roman Space Telescope and the next generation of ground-based observatories, promise to push these boundaries even further. These technologies will allow scientists to map the distribution of galaxies across cosmic time, study the chemical composition of early galaxies, investigate the role of black holes in early galaxy formation, measure the properties of dark matter and dark energy with greater precision. Philosophical implications. Beyond the scientific implications, these discoveries force us to confront deeper, philosophical questions about our place in the cosmos. If our universe is just one of many, what does that mean for the concept of uniqueness? If the Big Bang was not the absolute beginning, what preceded it? The idea of a multiverse, while speculative, has gained traction in light of these findings. If true, it would suggest that the laws of physics we observe might be specific to our universe, with other universes governed by entirely different rules. This challenges the notion of a singular, unified theory of everything and opens the door to a more pluralistic understanding of reality. Future directions. The coming decades will likely see a convergence of theoretical and observational efforts aimed at addressing these mysteries. Key areas of focus include: 1. Refining the Big Bang Theory. Scientists will explore modifications to the Standard Model, including the possibility of alternative mechanisms for galaxy formation. 2. Dark matter and energy. Understanding the nature and role of dark matter and energy remains a top priority. Are these truly fundamental components of the universe, or do they reflect gaps in our understanding of gravity and particle physics? 3. Quantum cosmology. The intersection of quantum mechanics and general relativity could hold the key to understanding the singularity that marked the universe's beginning. Concepts like loop quantum gravity and string theory may provide new insights. 4. Simulations and AI. Advanced simulations powered by artificial intelligence will help test and refine cosmological models, providing a virtual laboratory for exploring scenarios that cannot be directly observed. Conclusion. The universe, in its vastness, complexity, and mystery, continues to challenge and inspire us. The James Webb Space Telescope has opened a new chapter in humanity's quest to understand the cosmos, revealing a universe that is far more dynamic and enigmatic than we ever imagined. While the answers may still elude us, each new discovery brings us closer to unraveling the fundamental truths of existence. In the end, the pursuit of knowledge is as infinite as the cosmos itself. With every question answered, new mysteries arise, ensuring that humanity's journey of exploration will never truly end.